Way.
Okay, let me.
Đâu là ghi nó thu âm có gì ngồi đây nè cho mình nhấn.
Get my screen sharing here.
Yeah. Yes, got it.
And slideshow. Okay, everybody should be seeing this, I hope. Okay, today we're up to element 3 on the technician exam questions. Again, my name is Jim. AE7UQ is my call sign. I live in Bellingham, Washington, and I'm involved in emergency communications primarily, as well as some other radio stuff. So what today's topic is radio wave propagation. In other words, how does your signal get from here to there? What I'm going to do is go through sort of some of the basics. I have to say at the start that this is not my particular area of expertise. I've got an extra class license, but I live in a condo, and so I don't have a HF antenna. So most of my communications are UHF, VHF, and we'll go through that as we go through this, because we're going to talk about frequencies and wavelengths and that sort of thing as well as part of this section. So a lot of this stuff I don't have personal familiarity with, not having a lot of not being able to use HF, high frequency. So what is propagation? Radio wave propagation is a term we use to explain how radio waves behave when they're transmitted or propagated from one point to another on Earth. On Earth, yes. I'm going to review some of the things that we've had before. I think this has been in some of the, I know it was in section 2. Radio waves are like light. They travel at the speed of light in free space, approximately 300 million meters per second. You probably learned the English version of that in high school physics, 186,000 miles per hour. That converts to 300 million meters per second, or 186,000 miles per second. And then the formula you need to remember, and you'll use this an awful lot, is how do you convert wavelengths into frequencies? It's 300 over whichever you're trying to convert. So 300 over 2 meters, the wavelength, gives you the frequency, about 150 megahertz. And remember, these are all in megas, millions. And the reverse, if you want to go from frequency into wavelength, 300 over 150 would give you 2 meters. 2 meters is the wavelength. So this comes in handy. I refer to this all the time. If somebody says they're talking about one of the things and you understand it as another, you just have to divide it by 300 and that'll get you in the right place. Again, along the same lines, the frequency ranges, the 3 primary frequency ranges we talk about in ham radio, amateur radio, are the 3 to the right. HF, high frequency, from 3 megahertz to 30. VHF, very high frequency, from 30 to 300. And ultra high frequency from 300 to 3000. There's another chart here I'll get to, and we'll sort of talk a little about what's above and below those, particularly above as far as ultra high, super high, and things like that. And radio waves are electromagnetic waves, and there are 2 components in electromagnetic wave. The electrical part of it and the magnetic part of it. And those waves are both 90 degrees apart or opposite. So you can illustrate it in this chart here. If the electrical field is vertical, then the magnetic field is horizontal. And again, the points I'm touching on going through this front end is trying to hit the things that will be on the exam in some fashion. And so not trying to get in, this isn't a course on propagation, but mainly a course related to things you're going to see on the exam, because what we're trying to do is make sure that you're fully prepared for the exam and you will have seen all the questions after today. And hopefully you've seen them already in studying your part 3 in the book. Here's a lot of the specifics, and these are topics that are going to show up in various questions, and we'll talk a little bit more about some of them. And this is just sort of the different ways that radio waves can be propagated, and also some of the effects on the waves. Direct modes, basically line of sight, and multipath. There's quite a few questions on multipath, and that's pretty interesting. That's one of these things where you say, well, how did my radio signal get from here to there when there's all this other stuff in the way? And we'll talk a little about that. Atmospheric modes, ionospheric modes, others, we're getting up into the sky. And the waves can do all kinds of interesting things, the radio waves, once they get up into the atmosphere and start bouncing around, as we'll see. And there's various layers in the atmosphere. As it says, the F2 layer is the most important ionospheric layer for high frequencies. And again, high frequencies, when you see high frequency, think long distance. When you hear people, hams, talking about, well, I talked to somebody in Sweden or I talked to somebody in Australia today, they're using HF because the UHF and VHF don't have that range, and that'll be a factor in some of the questions that we'll see. And there's the FE layer, D layer, some other layers. And then there's something called sporadic E propagation, and that's sort of a special case, doesn't happen all the time. And there's something called tropospheric ducting. And so that's another one. It's like your radio wave is getting up into this nice little tunnel, traveling down the tunnel and then dropping out somewhere further away. Rain scattering, which waves might be affected by, or which frequencies really, what might be affected by rain. Diffraction, you can think about how a light wave can be diffracted by a prism. The same thing can happen with radio waves, and it's what we call knife edge diffraction. And absorption, some radio waves are more subject to being absorbed by things than others, and there's a question about that on the exam. So these are the general topics that will show up in the exam questions, and we'll talk a little bit now about what they actually are. This is a chart. It's kind of hard to read it all the way, but this is a more detailed chart that sort of goes through and tells you, as I said, we're talking, where did my mouse go? There it is. Here in the middle, HF, VHF, and UHF are what we're most familiar with. And this repeats some of the things we saw in the other one. In other words, when you're HF, you're into the E layer, ionosphere refraction, and the E, F1, and F2 layers. So these are the ones that were long distance communication by amateur radio. As a technician, when you get your technician class license, you'll probably be using primarily, which I use primarily in emergency communications, VHF and UHF, 30 to 300 megahertz and 300 to 3000 megahertz. And again, when you get down to the lower end, then you're pretty much in direct communication with a little bit of what we call here the tropospheric. And then when you get to super high frequency, and this is getting into the microwaves down at the bottom, the shorter the wavelength and you get into the centimeter range, the more subject it is to interference. Microwaves, when you get into microwaves, and if you stick around for the presentation after this, when you're getting into the gigahertz, all the phone companies now have their 5G networks. A lot of those, particularly in the networks, you really have to be able to have direct line of sight communication. Whereas at the other end of the spectrum, and we don't really have any amateur radio things down in these layers, when you're talking about kilohertz, there's very low kilohertz. It basically can go through anything. You can go through the earth, through buildings, that sort of thing. But most of our communications in amateur radio are going to be in the HF, UHF, VHF range. But there are some frequencies, if you remember that frequency chart I showed last week, if you were here for the last week, that sort of blue chart, there's a number of areas there. Amateur radio has frequency allocations up in the super high plus range, the 5G, 3G, or 5G and 2G in particular. So there's, depending on what frequency you're at, then there's different ways that your signal is going to get around. But the thing from long distance to remember is HF, short distance, UHF, VHF. Multipath. What multipath means that the radio wave is finding different ways to get from where you are to where you want, or from either the transmitter, if you're trying to receive something from a repeater, or you're trying to send something. You can see from this little diagram, there's several different ways that the signal can get to you by bouncing off other things. It's sort of like, think about the pool balls on a pool table. You can, any number of ways you can bounce, tear them off the side, the rails on a pool table, and get the balls in the pocket. It's not only one path. And the same thing with radio waves. There's any number of ways it can get there. And as a personal demonstration, you might say, this is my home location. I live in Bellingham, Washington, and daily I tune into a radio network, and that's it comes off a repeater in Mount Seymour in Vancouver, Washington, up north of Vancouver. It's about 55 miles as the crow flies from my location. And on the right here, you can see my antenna. It's about 4 feet tall. It's strapped to a tree on the south side of my condominium. And somehow the signal from my little antenna finds its way up to Mount Seymour and back, because I get almost perfect communications on the network in Canada with this antenna in this location. Whereas there's another repeater that I can communicate with less successful, about 3 miles from my house, about here where the E is on the home. And so you scratch your head and say, well, how come I can get into the repeater up here, but I can't get into the one, 3 miles from my house that I can almost see? Anyway, it's just what I call the mysteries of propagation. And a lot of times, if you start listening to radio nets, somebody will say, hey, Fred, you're kind of scratchy. Could you move a little, about 3 feet to your left? The guy comes back a little later, he's crystal clear, loud and clear, as we say. And so small changes can make a big difference. And then when we get into the other sorts of propagation, we said earlier, you've got sky waves, ground waves, and the sky wave here is used to demonstrate there's a question on elliptical polarization. And if it's direct line of sight or a ground wave, then you really need to have your antenna polarization alignment the same. In other words, you can have a vertical antenna or a horizontal antenna, vertical polarization, horizontal polarization. And what happens though, when you bounce a signal off the ionosphere, it'll get polarized elliptically. I'm not sure exactly how to draw that, but there's a question on that. So elliptical polarization, it's basically, it means you can have better success receiving that signal, even if it came off let's say a horizontal antenna or a vertical antenna. Once it's polarized, it'll have more flexibility, and you don't need as much of the polarization alignment. And as we saw, there's a lot of different layers in the atmosphere, in the ionosphere, and you can get all kinds of interesting effects and bounces in the way your signal moves through the atmosphere. Sporadic E is one I mentioned. This is something that occurs occasionally. And so you can see when this particular condition occurred, the guy who is here, signals coming up with the green, this guy used to be able to hear it, you'd get a good reception here, where if the sporadic wasn't there, it would bounce up again and you wouldn't get the same reception here. There's ducting, and we've got another picture on the ducting possibilities. here's ducting. Okay, the ducting is created by differences in temperature, and it's demonstrated here by with the transmitter here. Without the ducting, your ground wave probably wouldn't go any farther than here, normal range. But if the signal gets into this duct of warm air, it sort of funnels its way over to the receiver here, and you can hear it. And it's generally about up to about 300 miles range, I think, with the ducting. Whereas normally, if it's a UHF or VHF, you're not going to be more than 20, 30, 40 miles.
Jim, I would disagree with that distance.
Okay, well, go ahead. Disagree.
The
This is not
one
my area
time-
of expertise.
The one time that that's happened to me, it was about 1,200 miles.
Okay, yeah. As I say, I haven't known when I've experienced this since. Yeah, oh, good. Well, I say anybody else has got more experience, feel free to chime in. So we'll say up to 1,200. I think it. Well, yeah. Knife edge diffraction. This is what happens when, as I mentioned earlier, radio waves behave somewhat like light waves, and they can be diffracted. And in this example, to get over the hill, what might happen is there's some diffraction, knife edge diffraction, and so there will be some signal that will be received down here on the other side of the hill, even though it's not directly line of sight. Okay, that's sort of a quick overview of what we're going to try to cover as far as the questions, and hopefully most of the questions here you will see some reference. We've made some reference to the effects as we've gone through. There are some that again, I'm sure Steve will jump in, that I can't explain specifically, but and I said, there are always, I think we said before, there's always some questions on the exam that are best just to learn, and you may not need to understand the theory behind them. Okay, we're going to be talking about, in this section, are some of the radio wave characteristics we talked about, mentioned all of these sort of, and when we went through the first part. So what I'm going to go, there's 3 sections here. We've got sections A, B, and C. The total, I think, is 35 or 36, about 11 or 12 questions. And the way they set up the exam, you'll get 1 question out of each of these 3 sections on your exam. Out of your 35 questions on the exam, you'll get 3 from this section. But I can't guarantee which ones you'll get. Okay, starting off, why do VHF signal strengths sometimes vary greatly when the antenna is moved only a few feet? Well, I just gave you the example here. I've been on nets where moving a few feet makes a huge difference in the signal. Multipath, think multipath. Multipath propagation cancels or reinforces signals. So if you've got all these multipaths coming together, if you reorient yourself slightly, then you get a much stronger signal. The other water vapor, no, at this frequency, water vapor is not going to be, we're not going to be really into the ionosphere generally on these, so multipath is the answer. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings and obstructions are blocking the direct line of sight? Okay, we just saw that. Remember the little picture we just saw? Again, here we go again. Multipath. Try to find a path. It tries to find a path that reflects signals to the repeater. Again, moving a bit one way or the other. Again, change the path, and that's the answer. Multipath again. The other answers, well, horizontal and vertical. No, once you understand the question and you've seen an example, then it's pretty clear this is what you're trying to find, the multipath. Here's another example of multipath. Picket fencing is what it's called. What is the meaning of the term picket fencing? And typically what you hear is it's a rapid flutter of the signal due to multipath propagation. But what you hear a lot of times if you're driving along in a car with your radio, with a mobile radio, and you think about the train passing telephone poles on the rail, bip, 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 or you can hear a change, or you think, remember that multipath chart with going through the buildings. For example, if you were driving through a city and you had a path that was clear on the cross streets, then you would get an increase and decrease in the signal, a flutter in the signal. And that's what we call picket fencing. Sometimes on a network, somebody will say, hey, you got a bit of picket fencing, you must be driving along such and such. Again, multipath. What is a likely cause of irregular fading of signals propagated by the ionosphere? Again, irregular. Which of these? Okay, we saw that chart early on, all different ways that your signal can travel through the ionosphere, all these different paths. And that leads you to answer D, the random combining of the signals arriving at different paths. You can have the same effect in signals going up through the ionosphere as you can with the multipath on the more of the ground, multipath through buildings and other obstacles. So again, this is another instance of multipath. And here we go again. What effect does multipath propagation have on data transmissions? Now, in data transmissions, what you're trying to do at the end of the day is you're converting your radio waves into digital units, bytes, and then reconverting them back. And what you want to do is make sure at the end of the communication that all your bytes add up to the same number you started with. And if you've got different paths coming in, multipath again, well, you're going to have a more likely that all of the signal is not coming through the same path, and there's going to be slightly different time that the signal will arrive. And things like that, the multipath effect can create error rates that are higher than normal if you had a direct communication. So against the, again, understanding multipath leads you to that correct answer of D. Error rates are likely to increase. And what antenna polarization is normally used with long distance CW and SSB contacts? Now, we usually, as I said, talked about earlier, that most long distance, again, it depends on your definition of long, CW and single sideband, HF, these are typically HF, high frequency contacts, but we're talking about UHF and VHF here. And most big antennas for long distance, regardless of the frequency, tend to be horizontal, a long wire, a certain length, or what we call a Yagi antenna, which is a horizontal antenna. So the answer is horizontal. Steve may have a better explanation on that. Nope. Okay, and then what happens when antennas at opposite ends of a UHF or VHF line of sight? Again, when this is direct communication, remember that part of that one chart, that little picture we saw earlier, are not using the same polarization. That's the case where the signal strength will be reduced. Others, you're going to get the strongest signal when you've got the same polarization of the transmitting antenna and the receiving antenna. And that's the right answer. And which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? We talked about that when we looked at that one chart that explained how the polarization, elliptical polarization occurred. And so it said it's easier to receive, you might say, which is B. Either vertically or horizontally polarized antennas may be used for the transmission or reception. So it's sort of more flexible. And that's the answer to remember here. And I think this is maybe the last one. What is the effect of vegetation on UHF and microwave signals? Remember what we talked about earlier is that in that overall spectrum, the very high frequencies, microwaves, shorter wavelengths tend to be absorbed. In other words, trees get in the way and absorb it. These are the areas where it's best to have line of sight, particularly when you get into microwaves. Microwaves in particular, you want to have line of sight. And that's more subject to absorption by stuff, trees, whatever else. If you stay around for the Ham-Won presentation later on, that's one of the criteria for a Ham-Won connection is line of sight. And Ham-Won is up in the 5G frequency, or excuse me, yeah, frequency. Okay, and I think this is the last one. Now, again, this is another one where we just saw here that microwave signals absorption. What weather conditions might increase the range, decrease the range of microwave frequencies? Okay, absorption. Winds not absorb anything. Barometric pressure won't, colder temperature won't, but precipitation will. You've got stuff getting in the way, raindrops getting in the way of the signal. And basically, the inverse answer, you might say, what is the effect of fog and rain on signals in the 10-meter or 6-meter bands? Well, those signals are into the bands where you don't have to worry about the absorption, and they're not going to make a big effect. And so in this case, there is little effect. And so you're not going to have, your 10-meter signals are going to be just as good whether it's foggy or rainy or not. And which region of the atmosphere can refract or bend HF, VHF's radio signals? The ionosphere. And we saw that in one of the earlier charts. Okay, that's the first section. What did we have? 11 questions there. So one of these 11 you'll get on the exam. And this is a repeat of some of the stuff you should have had, we've had before. I know we talked about it in T1 and T2 in the past. Just things about frequencies, wavelengths, the spectrum. We just saw that, remember the little picture. What is the relationship between electric and magnetic fields in an electromagnetic wave? They're at right angles. Just remember that little diagram. The red ones are vertical and the blue ones are horizontal. And what property of a radio wave defines polarity? Polarity is associated with the electric field. And you just have to remember this. It's a sort of one that's easy to, well, it's one or the other, but electric is the polarity. And these other ones really don't apply. What are the two components of a radio wave? Again, remember that little chart, the red and the blue. We've got electric and magnetic fields that combine in the electromagnetic radio wave. We just learned this if we didn't already know it. What is the velocity of a radio wave traveling through free space? The speed of light. It sounds like it might be the speed of sound, but no, it's the speed of light. And there's no formulas associated. Well, these other ones, C and D, don't really apply. It's just the speed of light. And what is the speed of light? It's the same as the velocity of a radio wave, 300 million meters per second. As I said, you get this by converting 186,000 miles per second into meters, and that's what takes you to 300 million. And again, per second, remember per second, and the 300, if we remember, we'll see where the 300 comes from too. We already did. What's the relationship between wavelength and frequency? Remember the little formula, 300 over wavelength or frequency. And then if you just think about, you can do two simple calculations. Think about 6 meters, 300 divided by 6 equals 50. So the, let's see where we're figuring out whether we're on, so that's the 6 meters is the wavelength. And so if we go to 150, 300 over 150, 2 meters. So the wavelength gets shorter as the frequency increases. And you can just do a simple back of the envelope calculation if you can't quite remember. If you remember the 300 formula, 300 over the wavelengths give the frequency, 300 over the frequency gives you the wavelength, which is the next question. How about that? What is the formula for converting frequency to approximate wavelength in meters? Again, the thing to remember here is 300 divided by, 300 divided by. And all of the other answers here are something multiplied or divided by. It's not 300 divided by, it's something divided by 300 and multiplied by 300. So that's the easy way to remember this. It's always 300 divided by one or the other. So the wavelength in meters is 300 divided by the frequency in megahertz. In addition to the frequency, what is the following is used to identify amateur radio bands? This is basically most bands are identified by wavelength in meters, particularly in high frequencies. You say somebody say, well, I contacted them on 20 meters, or it's really terrible on 80 meters tonight, or yeah, 17 meters was really working well for me today. But when you get into UHF, VHF, for some reason, we talk about 2 meters, but then we talk about not 1.25 meters or 70 centimeters, we talk about 220 and 440. So those are sort of exceptions, but by common usage, that's how most amateurs talk about the 1.70 centimeters and 1.25 meters. And we saw the little chart earlier, VHF, 30 to 300 megahertz, VHF, you think about 150 as the VHF frequency, right in the middle there. UHF, 440, I just talked about 440. 440 is the UHF frequency, 440 megahertz, so that fits into the 300 to 3000. And the last one that we are most popular, HF, 30 to 300, 10 meters, 20 meters, 40 meters, 60 meters. So those are all in the HF range. Well, 60 meters isn't, a little over that, but certainly most of the, a lot of the popular ones are in 6, 10, 12, 17, 20. Okay, those are the, again, these are sort of the basics we had on frequencies, wavelengths, and you will have seen some of these before, I think. And again, these are the fairly easy to recommend. So this should be a fairly, you should be in pretty good shape on this section. So one of these questions should be pretty recognizable. And then the last section is when we get into the actual propagation modes, and we spent a little time on this, and I think most of the questions you can relate to what we talked about in some of the diagrams and pictures. Okay, so why are simplex UHF signals rarely heard beyond their radio horizon? Well, remember that UHF is one of those that is usually only propagated nearby, as it were. They don't tend, either if they get up into the atmosphere, the ionosphere, they disappear. They don't get bounced around and back down in the ionosphere. And they're generally used for short range. And so if we remember that, then you'll come to see they're usually not propagated by the ionosphere. And the other ones, regulations don't apply to something like this. And yeah, you could say they could be absorbed, but not reflected or refracted by the ionosphere. So the correct answer is C, not propagated. What characteristics of HF communication compared with communications on VHF? What is a characteristic? Well, we talked about this. Long distance, HF, long distance. Just remember that, and you've got this question nailed. It's not really to do with the antennas or bandwidth or atmospheric interference. It's long distance, the propagation on the ionosphere, long distance. As I said earlier, pretty much all HF, all long distance is HF. Again, depending on your definition of long distance. Again, Steve said earlier that he was getting up to 50 or 1,200 miles, I think it was, on one of the other modes. Okay, what is the characteristic of VHF signals received via auroral backscatter? We didn't talk about this specifically, but one of the things that can happen with the aurora is it can reflect the signal back down to you, just like you can reflect a signal off the moon or things like that. So there's all kinds of odd things that you can do with your radio signal. But the important thing here to think about is what does an aurora look like? Well, auroras aren't static. Auroras are moving. If you see pictures or videos of auroras, you know, there's sort of waves of colored curtains, things like that. And if that's what's reflecting your signal, what's going to happen to your signal? It's going to be distorted and it's going to vary in strength, and depending on how it's being reflected from this varying auroral display. They do awfully usually occur in the northern part of the world or the southern part where there are auroras. But really the important part here as far as the question is it's distorted because of the variable nature of the aurora. Which types of propagation is common? Which of the following types is most commonly associated with occasional strong signals on the 10 meter, 6 meter, and 2 meter bands from beyond the radio horizon? Now, this is one that I have to remember that the answer is sporadic E. If you remember that chart we showed that did show a little blurb and the map of what was called sporadic E, that the conditions in that particular area were good for bouncing the signal back down from the E layer. And sporadic E is that I'm not, it's not one of my areas of expertise, so I would just remember this one. We saw the little picture on NIFES diffraction. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? Remember that little picture we showed you with the mountain in the middle and the signal being diffracted off the edge of the top edge of the mountain? That's the knife edge diffraction. And so you still get some, you can receive, it'll be a lesser signal, but you can still receive the signal through diffraction, knife edge diffraction on the other side of the hill. And some of these are kind of odd answers. I'm not sure they mean anything. Quantum tunneling and Faraday rotation, I'm not sure that means anything. And the Doppler shift is something that happens, but not in this particular case. What type of propagation is responsible for allowing over the horizon UHF, VHF communications in ranges of approximately 600 miles on a regular basis? Okay, well, this is the one where Steve said he was more successful even further than 300 miles. But this was, you remember the temperature variations, and it created the duct in the atmosphere, tropospheric ducting, and that's the answer here. So it's the UHF, VHF, 300 miles, tropospheric ducting. What causes tropospheric ducting? Well, we just answered that. And if you remember the little chart, it showed you a band of warmer air between two bands of colder air in the atmosphere, which created the duct. And so it's temperature inversions in the atmosphere. So tropospheric ducting is related to temperature in the atmosphere, not lightning or sunspots or updraft from hurricanes. So that's temperature, troposphere ducting. Remember that. What band is best suited for communicating via meteor scatter? I have no idea. So I have to remember 6 meters. Maybe somebody else had an explanation of why meteor scatter is better at 6 meters, but I don't. So this is one I would say, just remember meteor scatter 6 meters. But again, meteors is another example of the various things in the atmosphere. We talked about the E layer, sporadic E, the aurora scatter. There's all kinds of stuff up in the atmosphere you can get bounce back from. And meteors, meteor showers, and meteors is another example. And this would be during a meteor shower. Which is generally the best time for a long distance 10-meter band propagation via the F region. Again, not having any experience in long distance 10-meter band propagation, I don't know from personal experience the answer, so I would have to memorize this one. From dawn to shortly after sunset during periods of high sunspot activity. So there's a lot built into this. It's knowing high sunspot activity versus low sunspot activity after, before sunset. Again, there's theory and reasons behind this, but from my perspective, as a not having done any transmitting on 10 meters, I would have to remember the answer on this one. So from dawn to shortly after sunset, high sunspot activity. Which of the following bands may provide long distance communications via ionosphere's F region during the peak of the sunspot cycle? Again, this seems to be similar. 10 meters is in the same category here. Again, I don't know the technical reasons, but again, the answer is 6 to 10 meters. And it's probably, if you remember where what frequencies are getting up into the ionosphere for the F and E layers, then you'll remember that 23 centimeters, 70 centimeters, and 120. This is 70 centimeters is 440, 125 is 220. And what have to calculate, you can calculate what 300 over 0.23 meters is. What's about 900 meters, or well, whatever. Anyway, I'd have to remember this one. And why is the radio horizon for UHF and VHF signals more distant than the visual horizon? Again, this gets back to remember it's similar to the little picture of the hill and the knife edge diffraction. And we know that radio waves are refracted in the atmosphere the same way that light waves are refracted in a prism. And so you get atmospheric diffraction, and that extends the radio horizon a bit beyond what the visual horizon would be. Dust particles, no, that doesn't work. This was getting into the theory of relativity. Radio waves do not move faster than the speed of light, and dust particles aren't a factor in this case. So the atmosphere refracts the radio waves. Just think in terms of those charts of the pictures of the radio waves bouncing around up and down into the atmosphere, and also the diffraction or the refraction. So that's the end of the questions, let's say you'll get one out of each of these three sections. From my standpoint, I had to study more for section 3 than I did for sections 1 and 2, or A and B. But as I say, one of these three, one out of each section will be on your exam. Any questions, ones that I can answer, hopefully? And if you do stick around for the ham one, which is going to be pretty interesting, you can think in the terms of some of the propagation questions that we've talked about here. And as I mentioned, ham one is usually is a 5G, 5 gigahertz signal. There's a specific section, I think 0.5, something to 5.9 in that range. These are allocated to ham radio, and that's where the ham one frequencies fit in. So you can, if you do listen to that presentation that Steve Kangas is going to give, it'll, oh yeah, I remember, we learned about that in the previous section. So any questions? Okay, well, I will stop sharing.
So Ray, can you stop recording?